Okay, so next we want to look at the gradient of scalar field. So what is a gradient of scalar field? So a gradient of scalar field is the extension of derivatives of a vector field. The outcome, the gradient of the scalar field will give you a vector, okay, a vector field which points in the direction. Okay, so this vector will have the direction, right? So this vector will give you the direction of the maximum rate of increase, or the greatest rate of increase of that scalar field, and the magnitude. Okay, when you have a vector field, you can evaluate the magnitude, right? So the magnitude of this vector field tells you the maximum rate of change. Okay, so I understand that as for now you don't understand what is the meaning of the gradient of scalar field. So I will show you on the next slide how can you have, or you obtain the gradient of a scalar field, so that you can have from a scalar field you can get the vector field, but you have to obtain or carry out the gradient of that scalar field first. So what is the formula or the process? So I will show you on the next slide. Okay, so the gradient of scalar field will give you a direction, where that direction tells you, by using that direction you are having something, the greatest rate or the maximum rate of increase, where its magnitude, when you obtain the magnitude of that vector field, so you can have the maximum rate of change. Okay, so for example, you have this example. So you can see that the black and white one is a scalar field, where when you evaluate the gradient of this scalar field, you can have the arrows. So that is called the vector field, right? When you obtain from the gradient of vector field, you can have the gradient of scalar field, you can have the vector field. So the blue one, the blue arrows, they are actually vector field, and as you can see, they are pointing to something here, right? So it means that so as you can see here, the above two images, the scalar field is in black and white. Okay, black representing higher value. Okay, this is higher than the gray ones. Similarly to this black, so the value over here is higher than something in gray. So these blue arrows corresponding to the gradient, okay, corresponding to the gradient of the scalar field, which it's point to the direction of the maximum rate of increase. Okay, so the maximum rate of change. So as for now, maybe you have no idea. So we look at how can we obtain the gradient of scalar field. Okay, as stated here, even though f is a scalar field, so the gradient of that scalar field will give a vector. Okay, so what does that mean? So firstly, you have to understand, you have to know what is the gradient mean. So the gradient of a scalar function f, so that is inward. Okay, gradient of a scalar function f is this one. Okay, so grad f, where grad is a short form of gradient. How can you explain this in language? So you can say the gradient of a scalar field f, scalar function f. So grad f is actually an operator. Okay, it's just like plus summation. You have the plus sign, you have negative sign, you have a division sign. What else? Multiply sign. So these are considered as operator. If just them alone, stand alone, it's nothing, right? Then they should have a partner. So for example, A plus B, and you will get some value. And similarly, A minus B. So you will have a sum value and so on. So similarly for the gradient f, so if you just have gradient without f, so it's nothing. Okay, so it should be partner with the scalar field or scalar function here. So okay, after they have the gradient f, so actually what's happened? Okay, so the gradient f means you can obtain a vector field from the scalar function f, which means that you can provide the x component, you can provide the y component, you can provide the z component. So what are the component about? So for the x component, you have to differentiate partially. Differentiate partially the vector function with respect to x. So that is for x component. And then for y component, you have to differentiate partially the vector function, the scalar function f with respect to y. And for z component, you have to differentiate partially the scalar field f with respect to z. Okay, and from there you can have a vector field after you differentiate partially the f with respect to each component. Okay, so that is a gradient f. So in this case, what is the grad itself, the gradient itself? So if we factorize the f, so you can see that del x, del y, del z. Okay, so this is operator. Gradient is in full. Grad is a short form of gradient, or you can also instead of you put the GRAD, or you can put the full name, you can also put that using a symbol which is called as nabla. Okay, so this is not delta. Delta you have this, but upside down you can have nabla. So what is nabla? Nabla is operator, which is gradient. This is called gradient, or that symbol is called nabla. So this is the operator of the gradient. So what is a gradient? So we can say that gradient can be considered as rate of change. So gradient of the vector function, of the gradient of the scalar function. So you can elaborate that as a rate of change of that scalar function, or you can have something about slope. Okay, but once you deal with the gradient of the scalar field, the outcome should be a vector field. Okay, why? Because the gradient here is actually the operator where you can convert from scalar field to a vector field. Okay, so that is a gradient. So now, how can we deal with the gradient of the scalar function? So first you have to have the scalar function or scalar field. Okay, so if you are given a scalar field, then you can find the gradient of the scalar field. So find the grad f. So we know that the grad f is the meaning of grad f is to find the gradient of the scalar field f. Or you can put in symbol where you have this one, nabla. Yes, how to sketch nabla? How to write down nabla? Nabla f, or gradient f at the specific point. Okay, so now how can you know that? Okay, based on your operator here, how can you know that you have to provide IG or IGK? So it looks like it depends on the type of function that you have. So in this case, it is defined that your function is in 3 variable function. Okay, where there are x, y, and z, meaning that you have to provide the component. There is I, G, and K, which is you must provide the component x, the component y, and component z. Okay, so in this case, we know that the gradient, this is vector operator. Okay, and then the nabla should have a symbol of a vector. Okay, so the gradient f will give you, so what is the operator? So del x, del y, del z, and then you have the f. Okay, you have the f where when you just like multiply. Okay, this is the operator and you have f is a scalar. So what you can have is del f del x, del f del y, then del f del z. Or you can use in a more simpler way, we have fx, fy, fz. Okay, so now your task is to obtain the partial derivatives of this one with respect to each of the variable. Okay, so for fx, differentiate all terms here with respect to x. So here you just have x, so you have 5 y z square minus 0, because you cannot see you don't see the x here, so here they are all constant. So now next fy, so fy here just have y, then differentiate y, we got y, so you have 5x z squared minus 2z squared. Okay, and then fz, so the first term you have z squared, so you have 10 xy z minus 4y z. Okay, so you already obtained the fx, fy, and fz, and then you evaluate each of the component by using the given point. So you have 5, y is 2, z is 9. Okay, and then this one you have 5, 9 minus 2, 9. And this one xyz minus 6, so 10 minus 6 minus 4 minus 6. So in this case you have okay, so when you evaluate you have 90, 27, and minus 36. Alright, so even though you have a scalar field, once you find the gradient of the scalar field, your answer should be a vector form. And if you know that you have to compute for some values, then your final answer should be a constant vector. Okay.